Hello. Okay, it's working. All right, so we're going to start a new topic today. Um, so hopefully the information complexity stuff we did rush towards the end, especially for the one-bit NAND. But I don't think that's the most interesting part. There you had to roll up your sleeves and do some calculations. You'll do at least some part of it in the homework, but or exam. But I want to talk about some other stuff for the next 5 lectures. Okay. So, today. Because we'll start a new topic, which can approach from many different angles. Which is a good thing. It's been studied in different fields and different forms. So I'll present kind of first the number on forehead version, which is the more communication complexity perspective on this question, and then we'll connect it to some questions in combinatorics. And finally, we'll talk about kind of a simpler case of this problem where there's a very clean algebraic technique called the polynomial method, and we'll see how to use it, right? And after I cover the polynomial method, I'll leave it up to you to choose whether you want to see more applications of the polynomial method or something else, okay? So you get to pick out of two options what you'd like to see for the last couple of lectures or so, right? I'll tell you, yeah. Once we set up the background, I'll tell you more, okay? Because if I just say it now, it will be too vague. So one important announcement, of course, is that exam 2 will be out tomorrow at 6 p.m. Okay, and it is due Feb 29th at 6 p.m. on grade school. All right. So you have 48 hours to do the exam, and it will be similar to exam 1 question. Oops, you're right. I'm not giving you 4 years to. Not that kind of an exam. Anyway, this Saturday. All right. Okay. So it covers basically the sensitivity conjecture lectures, sunflower conjecture, and information complexity, right? 7 lectures. And it'll be about the same or maybe a little bit more difficult than exam 1 because the median in exam 1 was 29 out of 30, which I'm very happy about, but still, just to make it a little bit more interesting for you. Okay. All right. And if you have any questions, please post them on EdStem. If it's a generic question, ask it directly on EdStem. If it's something like, okay, is the solution correct? Just make it a private post or reach to me by email. Okay. Okay. So let's start. So as I said, we're going to talk about this problem which has different origins. But let me talk about the origins from sort of number theory or combinatorics. And the specific area in combinatorics that it deals with is called additive combinatorics. Okay, and we'll connect it to computer science question pretty soon. And we'll see how kind of thinking about these questions algorithmically makes sense. And the question that was asked in 1936, really, by Erdős and Turan is, I give you an upper bound. Let's say n is some million or 10 million. And I say, okay, pick numbers from 1 through a million, but no three numbers should be equally spaced on the line. That's the only thing. So how big a set can you pick from 1 through n such that this set does not have three distinct numbers A, B, C that form an AP or arithmetic progression. Okay. And arithmetic progression just means that I have three numbers A, B, C such that B minus A equals C minus B, or equivalently, A plus C equals 2B. Okay. Obviously, if I take all three numbers to be the same, it is satisfied, but you want three distinct numbers, a non-trivial 3AP. All right. And we can just give some notation for this. So let's say R3 of n is max size of a set. S is subset of, let me use big N here. S is 3AP free. Okay. It's a little bit similar to how we define kind of, S of n comma k when we're studying sunflowers. Remember, we said, okay, how big a family can I, S of r comma k, where we said, okay, how big a family of sets can I have, where each set is of size k, and the family does not contain an R sunflower. Okay. There's a similar definition here, which is you're trying to see how many numbers can I pick while avoiding some pattern. In this case, the pattern is probably the simplest possible pattern, which is three equally spaced numbers. Now, one simple strategy you might think of is, okay, so let's say I ask you to pick these numbers. What's the first thing that might come to your mind? Any guesses? Don't try to be like, to the very end. So especially from an algorithm's perspective, if you've done CS180, one of the first things that you would try is greedy, right? I'll say, okay, I'm going to pick one, I can pick two, now I cannot pick three, because that would give me three numbers which are equally spaced. So cross out 3, and I pick 4. I can pick 5, I have to cross out 6, I have to cross out 7, and keep going. Okay? And it's a nice problem to figure out, how big a set you get using this. By definition, you are getting a 3AP free set, because you're saying, given all the numbers I picked, I'm going to add the next number, which doesn't give me a 3AP. Right? And you basically get roughly n to the 0.6, maybe some other decimal. Basically like log 2 base 3. There's another way to think about the set, which is, you take all numbers whose base 3 representation only has zeros and ones, or, something like that. Okay. All right. So the other thing you might try is, this is greedy strategy. If you're a computer scientist, you would try the greedy strategy first. If you're a combinatorialist, what would you try first? Random set, right? Okay, so this is greedy. And the other thing you might try is, let me pick a random set, completely random set. I'm trying to avoid this pattern, somehow prevent regularity. You might say, okay, maybe random set would avoid some regular patterns. Right? But actually, it's not the case. So if I try a random set, you can do a heuristic calculation. Right? So random set meaning, so let's say we pick S such that each element I is in S with probability P. Okay, let's just do a heuristic calculation and kind of guess how big a set you might get. Okay, now how many 3APs do we have? Over 1 through n, roughly n squared, right? You get to pick the first number, the second number, but then the third number is fixed once I pick the first and second. You might have some infeasible pairs, but that's okay. We're again doing a back of the envelope calculation. So we have roughly n squared number. And we have to miss all of them, right? And if given a specific triple ABC belongs to S with probability PQ, right? Because each element should be present in S with independently, and probability that all of them are present is like PQ, right? So that means that roughly speaking, the number of 3APs in S is going to be P cubed times n squared. Okay, you can make it actually rigorous and say that the expected number of 3APs in S is less than or equal to this much. Okay, but we want no 3APs in our set. That's our condition, right? So we're trying to avoid 3APs. So we want this expectation to be 0, in fact, or the number, this inner number to be 0. So in particular, we want this to be unlikely, right? And that will be the case if I set P to be something like n to the 2/3. Okay. Sorry? Oh, sorry, yes, negative. So if I set P to be roughly n to the minus 2/3, then maybe a little bit smaller. Then this expectation is like less than 1. So maybe some of the time at least I should see that there are no 3APs. Okay. Again, we don't have to do this calculation exactly. We're just trying to get an understanding of these things. So if we set P to be n to the minus 2/3, then how big a set did we get? Did I do this right? Yeah. So size of S is roughly n times. Oh, actually, I should say we don't want it to be small. We just want it to be less than n, because there are always n 3APs, right? Because there are the trivial 3APs which are always present, so you have to avoid them, right? So that's why you should actually, it's enough to take this to be this much. Okay, so this is roughly n to the 2/3. Okay, and you can argue that if I pick a set of size roughly n to the 2/3, you will get trivial 3APs, but not more than that. Okay, you have to be a little bit more precise with this calculation because you have to avoid the trivial 3APs. But again, we're just trying to get a rough estimate. Okay. So both cases, we're getting a number which is roughly the same, like 0.66 versus something n to the 0.6, maybe some other digit. But the point is that in both cases, it's polynomially smaller than n. Okay. So if n is 1,000,000, you're saying you cannot get much closer than like 1,000,000 to the 0.6. All right. So now the question is this the best possible? Or when can we actually guarantee that you'll start finding these sets? And this is a long history of being studied. So Roth in 53 kind of showed the first thing saying is n over log. Okay. In particular, one way to interpret this theorem is that if I pick any constant density set, let's say constant is 0.1, then at some point onwards, any set with this density will have 3-term arithmetic progressions, no exceptions. Okay, just because you have enough elements, you are going to find this structure. Okay, and then Heath Brown and Semereddy in 80s, 87 to 90, improved this substantially to this much. Okay, by substantially, you should really compare what's happening relative to capital N. Capital N is always there. It's like earlier we only had 1 over log n, now it's like 1 over log n. So exponential improvement in the deficit in some sense. Okay. And then somehow we started having smaller gains. Bourgain, in some important works which laid the foundations for many subsequent techniques, kind of improved the exponent to be log n to the 2/3. And Sanders in 2011 got it to okay. So you have 1 over log n. So it's pretty nice that even little of n size sets, even things which have sublinear density will contain this pattern. Okay. There's a lot of other work that I'm skipping, but I'm only mentioning things which might show up later on depending on what topic you pick. Okay. So, and then Bloom and Sisask in 2020 showed that, in fact, even sublogarithmic sets must contain this pattern. Okay, so like C is like 0.01 maybe. So let's say, so then it's saying that even sets which are n over log n to the 1.01 must contain this. And qualitatively or quantitatively, there's not, maybe you could argue, there's not much of a difference between this bound and this bound, but it makes a big difference qualitatively. Okay, there are a lot more interesting sets which have this density than that. Okay, one such example, one such famous example is that, for example, this immediately implies that prime numbers prime numbers contain infinitely many 3-term arithmetic progressions, not because prime numbers have some special properties, they do, but just because the density is more than 1 over log n to the 1. Okay, the density is roughly like 1 over log n times 1 over log n or something. So some little of 1 over log n. So, but this is where it hits. You couldn't use Sanders's result to get it, but now you can. Okay, and I mean, this is how things stood, but there was also this beautiful construction, which I'll talk about, from 1946. Okay, so Behren in 1946 showed that R3 of n is at least n over 2 to the c times square root. Okay. So again, as I said, always compare in terms of the deficit capital N. Right? So the capital N is always there. So now we know that things which are roughly 1 over log n or 1 over log n is 1.01 must contain a 3AP. And there is a set which has density 1 over 2 to the root log. Okay, it's kind of a weird number, 2 to the root log n. We don't see that often, but in some sense, there is still an exponential gap between these two. Okay. And so a couple of years ago, me and Xander Kelly got close to closing this gap. And what we showed was that Barron's example is likely the right answer. Okay, so earlier it was like 1 over log n. Now it's 1 over 2 to the log n to the 1/12. Okay, this 1/12 has since been improved to 1 over 7, I think, or maybe 1 over 6 now. But it does suggest that Barron's construction from 46 is probably the right answer. Okay. So we had this big gap, now it's closer. And what I want to do over the next few lectures is first talk about this construction, how it connects to a problem in communication complexity, and then depending on what you choose, either talk about this or something else. Okay. But in between, I'll also present an easier version of the same problem, which has a very simple but beautiful proof. Okay. Any questions about the problem or kind of the history? Okay. It's a really easy problem to state, right? All you're saying is, to understand the question, you don't need anything beyond arithmetic, right? That's why it's so appealing, I think, and that's why many people have tried it. But it kind of underlies, it hides many difficulties in that problem. Okay? And you'll see why in a second. All right. Let me, and then of course you can also talk about, there's also our K of n. Okay. We're only talking about 3-term arithmetic progression, but 4-term arithmetic progressions, 5-term arithmetic progressions. And of course, people have studied all of that as well. Okay. It's a lot of work on those too, but we won't talk about that at all. Especially Semmelweis theorem, which was a landmark result in 75, and then Gowers in 98, 99, and so on. Okay, but we won't be talking about any of this. I'll just focus on R3 of n, even there a smaller set. Okay, yeah.
You don't expect your methods to help with RK of n?
I mean, they can potentially. There are some intermediate problems that we've been trying, and in some sense, if you want to get this style of bounds, this is the only technique that we have. And R4 of n especially seems, I mean, I don't know if everybody agrees, but at least to me, going from 3 to 4 is the big step. Going from 4 to next is maybe a smaller step. Yeah. All right. There's something that changes drastically when you go from 3 to 4, but after that, it's maybe a little bit more doable. Okay. So as I said, it's a very simple, elegant question. Why 3 APs? And we'll see it has some direct applications in communication complexity. And also to parallel repetition, which is another important problem in complexity and algorithms. In fact, we got interested in this problem because we were studying parallel repetition, which I can talk about some other day. It's definitely a greatest hit, but it takes more than 3 lectures to cover. It's a really, really beautiful result, very counterintuitive. And we're working on some special case of the problem, and that's how we started working on this. But there are some intimate connections between these two things. Okay. But also, as has been the case throughout, we've been using like one sort of flagship problem to learn some techniques, right? Some methods or introduction to broader area. In the same way here, this problem is kind of very nice for studying methods which are usually called structure versus random. And also the polynomial. Okay. All right. So let me first, maybe this is what we can probably do today, is focus on this connection. Because again, this is really a rabbit out of the hat connection. It's really beautiful and connects to this Behrens construction from 1946. All right. Okay. So the first thing we're going to do is understand this construction. So we saw greedy, it got stuck at n to the 0.6 something. Random, also something similar, n to the point something. But how did Behrend get this n over 2 to the root log? Okay. It's a weird number, as I said, 2 to the root log n. But now we strongly suspect that is the right answer. In fact, it has to be of something of this one, log n to the 1/12 versus log n, root log n. Okay. Okay. So let's talk about Behrend's construction. So what are we looking to find, right? So we want a set S subset of n as big as possible such that there are no solutions to a plus b equals 2c. Okay. There are no solutions, there are no triplet of numbers which are distinct and satisfy the equation a plus b equals 2c. Of course, if they are all the same, it's trivial, but we want something which do not satisfy this equation, yeah, there are no solutions which are distinct. Okay. And the punchline for Behrend's construction really is the following geometric fact. Right. And okay, so if I take a sphere, right? So we were talking about integers and so on. Let's talk about just points. We have just arithmetic, right? I can ask this equation for vectors also. Okay. So let's say I tell you, find a set on, like, let's say R2, which has no solutions to a plus b equals 2c. And my claim is that if I ask you to pick points on the unit circle, then I cannot find 3 points ABC in the unit circle such that a plus b equals 2c. Okay. So if this is A and this is B, then a plus b over 2 is going to be in the interior of the circle. So it can never be on the circle, right? Unless they are exactly equal. Okay. Right. And the same point or same concept generalizes to higher dimensions as well. Right? So a line will intersect a circle in only 2 points. It cannot intersect in 3 points. And the same holds even for higher dimensional sphere. Right? So that's the punchline. So if you take unit sphere in d dimensions. Okay, so this is SD minus 1, which is all x 1 through xn, xd, sorry, such that summation xi squared equals 1. Okay, this is my set. Then SD minus 1 does not contain distinct points x, y, z such that x plus y equals 2z. The reasoning is the same. I take 2 points on the sphere. Their midpoint is going to be in the interior of the sphere. It cannot be on the sphere. Okay. So in some sense, we already found kind of a big set, right, which contains no points, no triplets which satisfy the equation x plus y equals 2. Okay. And what Behrend did after this is basically map this set to the integers by some map. Okay. We found a big set which does not contain any such solutions. We had to find a way to map these points to the integers while respecting this arithmetic. Okay. All right. So that's the, I think once you have this insight that, okay, I have already found this big set which does not contain such solutions, finding the mapping is some calculation. Okay, in particular, this is how it went. We're going to fix some range K and a dimension D. We will pick these parameters pretty soon. And let's look at all points. So all D tuples where each coordinate is a number from 0 through K. Okay. And let SR be, let me call this K. I'm including 0, but that's fine. It doesn't really matter. Actually, you know what? Let me not confuse you. Okay. So what am I saying? Fix a radius R and look at all points which have integer coordinates and lie on a shell of radius exactly R. Okay, so eventually we want to get points on the integers, right? We had to map things, we have to get points from 1 through n. So let's first try and use this idea to find a big set of points which does not contain solutions to this, but all coordinates are integers. Okay, maybe if all coordinates are integers, we can then map it back to a single integer number as well. Right? And whatever is said here also holds if I replace this one with some other number. It's just scaling it up, right? Even if I say, okay, look at all points which lie on the sphere of radius 1000. Since they lie all on this same radius, you won't have solutions to x plus y equals to 0. Okay. So let's look at this set SR. Now, just from this same logic that we had, SR does not contain solutions to x plus y equals to 0. If I take 2 points, their midpoint is going to be on the interior, its radius is going to be smaller, so it's never going to be on the same set, in the same set. Okay? So claim they do SR has no distinct points x, y, z such that okay. So at least we have some sets which have integer coordinates. They're still sitting in high dimensions, but they don't contain solutions. The second thing we're going to do is to argue that one of these SRs must be big. Okay. For every R, the shell of radius SR does not contain solutions to x plus y equals to z. But if I set R equals 1, I will only get a small number of points, right? Because I want integer coordinates. In fact, there'll only be just like D points which satisfy. But I'm saying there is some radius where I get a lot of points which satisfy this equation. Okay. And why is that? Why do you think this is true? Any suggestions or guesses? Why should there be a radius which has a lot of points on that shell? So just imagine I'm drawing these shells, right? You know, radius 1, radius 2, radius 3. Of course, all of this is happening high dimensions. But I'm saying some shell must have a lot of points. Okay, why is that? It's some kind of averaging argument, right? So how many points do we have in total? Okay, so if I look at k to the d, there are k to the d points, right? And every one of these points, x belongs to k to the d, has summation xi squared less than or equal to d times k squared. Okay? So if I just keep drawing these shells, all of these k to the d points must lie in, we have k squared times d many shells, right? And there are k to the d points in total. Every point should lie on one of these shells. So at least some shell must have more than the average number of points. Okay. So implies there exists R such that size of SR is at least k to the d divided by k squared. Okay. So let's fix this R, which has a lot of points on that shell. So summary, we have some shell. Again, this is in high dimension, so I'm drawing it in 2D, but that's fine. So SR is x belonging to k to the d, such that summation xi squared equals R. And we know that this set is pretty big, almost exponential size. Okay. How can I map these back to the integer? The claim is now we can map these numbers back to the integers such that kind of respect the equations. Okay, meaning yeah. Because the numbers are integers, right? So the xi's are all integers. So the summation xi squared must be an integer. But it's at most k squared times d. So there are only k squared d options. Okay. Yeah, so we're kind of using the fact that even though you have many points, since the distance from the origin, the sum of squares is an integer, they should collide. Okay. Question or?
Is this averaging argument, it's like the best you can do, or you expect
It's pretty much the best. Like, you can, unless I think you have some very pathological cases, it's asymptotically right. Okay, so now we have points on a shell, which do not have solutions, of course. But you're in the high dimensional case. So we have integer coordinates, 1 through k, but you have d coordinates. Now, how can I map them back to the integers? I want to map them back to the integers while kind of maintaining this property that if I have no solutions here, then I should also not have any solutions in the new things that I'm writing down. Okay. So in some sense, I want to say that when I map it to integers, addition in this space is the same as addition in the vectors. So f of x plus f of y equals 2 times f of z, if and only if the same equation held for these vectors x, y, z, which were in k to the d. Okay. So how can I do this? What kind of mappings can I use for this? So I have a vector, I have a vector, I have a vector. I want to map the vectors to integers such that addition of vectors corresponds to addition of integers. Any suggestions? No? Think like a computer scientist, maybe. We do this all the time as computer scientists. In every algorithm, every time we do any computation, this is exactly what's happening. How do you map vectors to numbers and numbers to vectors? How do you do vector addition through numbers? So, sorry? Basically, we can view this as some kind of, like let's say you have binary representation, right? A number in binary representation is really a vector. Okay. And in more or less, addition of the numbers corresponds to addition of these vectors. Of course, we might have some carryover issues, right? So if I avoid carryover, then vector addition is exactly just number addition. Okay. So how can we find this mapping? The point is that we have each point x is so let's say x is x1, x2, all the way up to xd. Okay, every number is from the range 1 through k. And I'm going to view this essentially as the base 2k plus 1 representation of a number. Okay, so view x as a base 2k plus 1 of a number. Okay. Right. So what does this mean concretely? So we are saying f of x is exactly summation I equals 1 through d, and okay, so this is the map. I'm going from x, which is a vector, to this. Okay. So if k is, for example, 1, then you're just saying I'm writing a vector whose coordinates are like 0 or 1, and I'm mapping from that to, I'm viewing that vector as a number by writing it in ternary representation. Okay. Coincidentally, this is what the greedy construction gives you. Okay. So, all right. And so that's it. So we have a mapping now. And the point is that if f of x plus f of y equals 2 times f of z, then we should actually have exact equality because there is no carryover. Xi is in the range 1 through k. Y is in the range 1 through k. When I add them up, I'm not getting a carryover to the next one, right? So this happens if and only if x plus y equals 2c. Okay, you can write it down more carefully. So f of x plus f of y equals, it's a number. Okay, all of these things are in the range 1 through 2k now, but it's still less than the base representation. So it is actually the base representation of the number, which is unique, right? So whatever base you pick, like if I want to write a number in base 13, it has a unique representation, right? So, and 2 times f of z equals this. So these two are okay, so we need to have this x plus y equals to z. Okay, all right. So now we have to figure out, okay, what's the parameters, what range are we getting, and so on, right? So we have a bunch of numbers. We have, basically we said, okay, we have this high dimensional set. We went from there to the real line, and we got integers, in fact. Maybe not all, but you might get some point here, some point here, maybe some point here, some point here, and so on. Okay, we got such points. Okay. And we know that they do not contain a 3-term arithmetic progression. Right? So we have to figure out how many numbers did we get and what's the range we are going up to. Okay, how far along the number line did we get? And related to that, how many numbers did we pick? Okay. So let's do that. So we want to say that f of SR is subset of n for some n. And if x belongs to k to the d, then f of x is less than or equal to, let's write it down. Okay, so every such number is going to be at most 2k plus 1 to the d, and this is what I'm going to call capital N. Okay, I'm defining capital N to be this, right? So no number that we write down is going to be bigger than this. Okay, so if you go back to this map, if you set n to be 2k plus 1 to the d, every number that we write down is to the left of it. Okay. Right. And how many points did we pick? The number of such points is at least k to the d divided by k squared times. Okay. Which is roughly n divided by 2 to the d times k squared times. Okay. And you have to do some optimization here. Like you get to choose what is k, what is d. Right? You might say, okay, I'm going to pick k to be very small. Like let's say k is 10, then d is going to be very big. So somehow this 2 to the d is going to give a big hit, right? If I choose k to be very big, then d can be small, but this k will hurt us. Okay. So if you balance these two things, you essentially get, okay, the right way to balance it is to set up to, let's forget the constants, but you can set this to be something like this. Okay. So if I set k to be roughly equal to 2 to the d, that's when we get the right. Okay. So in which case, the size of the set is at least n over 2 to the c times square root log for some fixed c greater than 0. And you can figure out this constant as well. Exactly. Okay. Any questions about this construction? We kind of started with a simple geometric intuition that at least in high dimensions, I can find such sets. And then we just map them to the integers by using some base representation. Okay, yeah. Yeah. That's a good question. I mean, I don't know. It's coincidence to me that it happens that, greedy actually gets you the same thing. Okay. And okay, so So to understand why is greedy gets you the same thing, you should start, instead of starting from 1, let's say start from 0. Okay, so you pick 0 and 1, then you avoid 2. Okay, and then you start figuring out that, okay, so every number you pick only has zeros and ones in its base 3 representation. So you're ending up with the set which is only basically 0, 1 to the n, but it's in base 3 representation. Okay, which is what this is giving you, but it's somewhat of a coincidence. But it'll be nice if there is an interpretation of this as some kind of greedy thing. Because, if you look at this construction, until a few years ago, I always said this is somewhat ad hoc, right? You said, okay, I'm going to find this in high dimensions, and then I'm going to map it to integers by some base representation. And magically, you got the square root log n, that's the right setting of parameters, and nothing else fits, right? But now we kind of strongly suspect that that's the right answer, and you cannot do better than this. So if there is a nicer way to understand this, I think that will definitely be helpful. Okay, yeah.
So if this is sort of based on the fact that you can find a sphere large enough for which there are a lot of lattice. And so is there a way to so is it that we can perhaps improve if we can find some pathological example symptotically where we have a lot of that? Or is this like not?
I mean, I would suspect not. Like, in fact, the true answer should be n over 2 to the root log n. Okay, we know it's at least n over 2 to the log n to the 1/7, right? And presumably, if some other conjecture is true, you already get to 1/3. So, strongly suspect the answer is 1/2. Okay. All right. So, we kind of saw one example of this nice construction, and let me now talk about an application of this construction to an algorithmic problem. Okay, and there are many applications of this, surprisingly, and we'll see one application of it, and then we'll start talking about how we can prove stuff about this question. Okay. All right. So the application is going to be, again, to communication complexity. We already talked about it. So okay. And in particular, we talked about kind of the equality problem earlier, right? But I'm going to change the notation a little bit so that the connection to what we discussed is clearer. So we have Alice and Bob. As usual, Alice gets some input X, Bob gets some input Y, and we're trying to compute some joint function of their inputs, right? But now let's view their inputs as some real number from 1 through n. So some integer from 1 through n. And same for Bob, okay? Of course, if you're thinking of bit strings, we can map them to integers by just viewing it as a binary representation, right? So then capital N will be 2 to the little n, where it's like an n-bit string, okay? And they're trying to compute some function. Let's say it's even a Boolean function, okay? We already talked about the equality function, right? So equality means I want to check if x equals 1. A closely related thing to equality, and which is I'm going to call checksum, is again, I'm simplifying the problem just so that we have something concrete to work with. I'm interested in one specific function, which I'm going to call checksum. So I have a number x, you have a number y. I want to check if x plus y equals capital N. You can replace capital N with any other thing. The complexity doesn't change. You just want to check if they add up to whatever target that we have. Okay. And what's the complexity of this problem?
So what's the communication complexity of checksum? And we are only interested in the deterministic communication complexity. Okay. So remember, for equality, we said there's no better protocol. If I want to check if x equals y, you really have to send the entire string x, right? And checksum is basically equality in disguise. And I'm just checking the equality of x versus n minus 1. Okay. So the communication complexity of checksum is also going to be exactly log n base 2. You cannot do anything better than sending my number across. Sending my number across will basically take me log n bits of communication because I can send the binary representation. Okay. So this is well understood, all done. Now let me try and generalize the problem to say, okay, what if I don't just have two parties of communication? Someone asked this earlier as well, but I have three parties who are trying to communicate. So Alice, Bob, and now we also have a new character, Charlie. So there's Alice, Bob, Charlie. Okay. So you get X, Y, and Z. Okay. And the usual sort of modeling applies. You know, I have three parties and I want to compute, and they can communicate with each other. You can assume broadcast communication or any, like, maybe even just specific links. Either way, these are all equivalent up to constant factors. So let's just say that they're all communicating with each other. And at the end of the day, they want to compute some joint function of their inputs. Right? So f of x, y, z. Okay. And you can ask what's the communication complexity of any problem in this more general setting, like 3 players, 4 players, and so on. Right? And the specific problem, again, that we're going to talk about is kind of the 3-party version of equality. Okay, so the easiest version is to say I have x, y, z, and I want to check if x equals y and y equals z, but that doesn't somehow couple the multi-party nature of the computation. It's breaking up into 3 separate problems, right? But instead, the checksum problem is nice. It kind of was equivalent to equality in the 2-party case and extends to 3 parties in a natural setting. Okay. Once again, just think you have multiple servers, you have multiple hashes. Running checksum is an important process for all kinds of system checks. Okay. So we ask for the same function, which is checksum. Now for 3 players or parties. Okay, they want to check if the sum adds up to capital N or 0 otherwise. Okay. If capital N bothers you, you can really think the numbers are between minus n through capital N, and then you just want to check if they add up to 0. Okay, either way, it's fine. It doesn't matter what you put on the right hand side. Okay. And it's not too difficult to show that for 3 players, you don't get any advantage, right? So meaning, there's a little bit more work, but not too much, to say that the communication complexity of CSUM, checksum, again with 3 players, is equal to some constant times log n. Okay. It's at least log n, and it's at most 2 times log n base 2 plus 1. I'm just specifying it up to constants because I didn't say whether you're using broadcast communication or specific links. And that can change the model a little. Up to constant. Yeah? Exactly. It's basically saying that you have to send the entire input. Okay? And this, when we talk about multi-party setting, usually when each person has their input, this is called number in hand. I have my input, you have your input, some other party has their input, and we're trying to compute. Okay? But then there is this twist that we're going to throw. And it's a beautiful twist. Okay? And I'm going to say that the players, instead of having the numbers X, Y, Z, kind of, have inputs, they have their numbers on their forehead. Okay. What does this mean? Have you played this game before? Camping or something where you have some celebrity's name written on your forehead, or basically a card, and then you have to guess what that person is, who that person is, by asking questions to the other, right? So in some sense, you can see the other people's inputs, but not yours, right? So Alice can see Y, Z. Bob can see X, Z. Charlie can see X, Y. Right? And you can ask the same thing, what is the communication required in this model? Okay. So if I have a function f from taking 3 numbers to 0, 1, I can say this is called the number on forehead, or NOF communication model. It was introduced by Chandra, First, and Lipton in 83. Okay, question? Okay, so you change who sees what, but the model of communication after that is the same. When they communicate broadcast or channels, it doesn't. Okay. So first things, it seems like a toy or kind of a very, puzzling model. Why would you think of such a thing? First, it has amazing number of applications in data structures, algorithms, lower bounds, circuit complexity, parallel repetition, combinatorics, and so on. Okay. But also, you should think of it as a model of communication where you have different parties, they're holding some databases, but the main thing is that there is overlap in their inputs. This is kind of an extreme form of overlap, but it's saying no party holds all of the input, but they need not be disjoint. You can ignore the fact that they already share some information and behave as if they don't share some information and run your previous protocols. But if you know something about the shared information, can you use that to your advantage? Right? So for instance, if I go back here, you can say, okay, Alice is just going to ignore Charlie and pretend she only knows Y. Bob can say, I only know Z. Charlie can say, I can only know X. So this way, this model can simulate the previous model for sure. Right? It's stronger. But the point is, if there is some shared input, can I exploit that? There are some shared inputs, but it's not so much that I can do all of my computation on my own. Right? So you have different databases. Maybe half of the records are shared. Can you use that to your advantage? Okay. All right. And it turns out, in many cases, first, understanding number on forehead complexity is kind of very difficult. Okay. But also, you have some surprising protocols that you can build. Right? In particular, this paper, Chandra, First, and Lipton from 83, they really pulled a rabbit out of the hat and showed that the number on four-head complexity of checksum is of square root log. Okay. So without number on forehead, the complexity was log n. Okay, so you're getting quadratic savings. Okay, does it make sense? So you're getting to go from log n to square root log n. All right. Any questions about the statement? How did they do this? They used Beheren's construction of all things. Okay, that's why I said it's a rabbit out of the hat, in the sense that this question doesn't seem to have anything to do with three-term arithmetic progressions. One is talking about patterns in numbers. This is talking about, okay, do these three numbers add up to capital N? Okay, so let's take a 5-minute break, and when we come back, I'll talk about this protocol and how it connects to the 3AP problem. Okay, all right. Okay, so this is not, I mean, what did they actually show? They showed something pretty generic. They said is actually log n by R3 of 6. Again, I'm being lax with the constants to simplify the presentation. So if I find a large 3AP free set, I get a protocol which takes few bits of communication. They didn't have to exactly dig into what construction Beren had, but they just needed some big 3AP free set. Right? And if you plug in Beheren's construction, then of course R3 of 6n is roughly n over 2 to the c times log n. Right? So this becomes square root log n. Okay, log of 2 to the root log n is O of square root log n. Okay, so that's how they get this. All right. And another sort of way to interpret this is if I show that the NOF complexity is little omega 1, meaning it grows with capital N, it's not a constant. Showing this is highly non-trivial, because this implies that constant density sets have three-term arithmetic progressions, which is like, Roth's theorem. Okay, so you have communication problems saying that it grows with n, the complexity grows with n, requires some deep math. And a priori, it sounds like a very simple question. Check if x plus y plus z equals n. Okay, that's kind of the surprising. That's why I said, it hides a lot of magic inside this simple definition. Okay, implies that sets of constant density over n have 3 APs. Right? And the same thing holds for higher dimensional. Like if I have 4 players, then yeah, it gets harder. It corresponds to 4-term APs and so on. Okay, all right. So how do we prove this claim, this construction from Chandra, Parson, Lipton? They said, okay, give me a 3AP free set, right? Have set S, which is subset of n, and size of S is roughly R3 of n, as good as we can expect, right? They said, okay, S is 3AP free. I need something slightly stronger than a 3AP free set. But if you give me a 3AP free set, then I can construct what I'm going to ask for next, right? So what I'm going to ask for next is the following. So think of what we said was the 3AP free set, right? You know, you have points 1 through this integer points all the way. Okay. And I'm picking a set. You know, with many, many points, you know, as many points as I can, such that there are no 3 APs within this set. Okay, if I plot them out, this is what it looks like. They said, okay, don't just give me one set, but give me different sets. Okay, none of which contain 3-term arithmetic progression. Okay, concretely, they said, what I really want is a coloring. Give me a way to color the numbers from 1 through n with as few colors as possible, such that there is no monochromatic 3AP, meaning there are no 3 numbers which have the same color and form a 3-term arithmetic progression. Right? That is, they do not exist A, B, C such that A plus B equals 2C and chi of A equals chi of B equals chi of 2C, chi of C. Okay. Like these blue colored points, they're all of the same color, but we know that there are no points A plus B equals 2C. Okay, so at least we found one color class, right? So they say, okay, I don't just find one color class, I want to find many color classes, but as few colors as possible. Of course, if you don't put a constraint on the color, I could make each point its own color, right? And it's not too difficult to show that the number of colors required is very related to the size of a 3AP free set. Okay, and I'm not going to prove this, just some randomization argument or a greedy argument even. Okay, so if we have a coloring which has no 3 monochromatic, no 3AP which is monochromatic, then at least one of the color classes must have size n over delta n. If I use 10 colors, at least one color is getting 10% of the elements. And since it is since there are no monochromatic 3APs, each color class is 3AP free. Okay, so this is just from kind of by definition and averaging. This requires some work, but there's almost a tight relation between these two. Okay, there's a generic tight relation. You can also go back to Behrens' construction and basically come up with a color. Okay, just change, you look at the construction, look at the points, and from them you can construct a coloring. Okay, so both can be done, right? So what does this mean in particular? So this implies that I can have delta n be so there is a way to color the numbers from 1 through n with 2 to the root log n colors, okay, such that no 3 numbers with the same color form a 3AP. All right. Okay. So let me write that down. And let me call it Behrend plus or 2.0. There exists a chi from n to 2 to the some other constant times log n, such that there is no monochromatic 3AP. Okay. So this is the abstract item that we would need for building the protocol. Right? But still, it seems weird that you're trying to solve checksum, but how does this abstract coloring come into play? Right? That's why I don't know how they came up with it. I think it's a really ingenious construction. But when I write it down, you'll see it's just a few lines. Okay, so there's Alice, Bob, Charlie, and we know Alice has X, Bob has Y, Charlie has Z written on their foreheads. Okay, and what do they want to do? They want to communicate and check if X plus Y plus Z equals N. Right, so that's the protocol that they're trying to solve. That's the function that they're trying to compute. Okay, so now the point is that, okay, this is true if and only if I'm going to break the symmetry for no reason than to simplify notation, but okay, if and only if, let me just write this as this. Yeah, no, I don't think I need to do that. Let me just call this difference D. Okay. So you want to check if X plus Y plus Z minus N equals 0. Okay, let me call this number D. Okay. Think of it as the common difference of a 3AP that we're going to build. Okay. So what is Alice going to do? Alice is going to look at a specific number which only depends on what she sees, right? That specific number is minus Y minus 2Z. Why this? Just play around with it and you'll find it. Okay. And what does Bob going to look at? Bob is going to compute minus Y minus 2Z plus D. Okay. And Charlie is going to look at this number plus 2D. Okay. These three numbers form a 3-term arithmetic progression, right? So I'm adding D and then 2 times D, so the gap between them is the same. Okay. But what is this number? What is minus Y minus 2Z plus D? I mean, it's not important what it exactly is, but what does it depend on? Does it depend on Y? I have minus Y, but then I have X plus Y plus Z there, so Y gets canceled, right? So this is just X minus Z minus N. Okay. And this is just, let me write it down here. Okay. And this is 2x plus y minus 2n. Okay. So what happened here is Charlie's number, whatever Charlie is supposed to compute, only depends on X and Y. Doesn't depend on Z, because we don't want it to depend on Z. If it depends on Z, we are in trouble because Charlie doesn't know what Z is. Same for Bob. It only depends on X and Z, what he can see. Same for Alice, Y and Z. Okay. Of course, we have one annoying issue that these numbers are between, they can potentially be negative, right? So let me just offset them to avoid this and put 3n here, 3n plus, and 3n plus. Okay, so that I have every number between 1 through something. Okay, it's non-negative. Right. So now what are they going to do? They compute these numbers. They know what they are. Each one can compute them based on what information they have access to. Right. So what's the last thing that Alice is going to do now? She is going to announce the color of the number 3n minus y minus 2. This is something from 1 through n. He's going to say, okay, what color does it have? From Behrend plus, we have this chi, right? I'm going to look at the color that this coloring gives to this specific number. And same for Bob. Bob is going to say, okay, tell me what color does, n 2n minus x minus z plus, I guess. Charlie also is going to say, what is the color of n plus 2x plus 1? Okay. So the communication is only the color. So Alice announces the color of 3n minus y minus 2z, Bob the color of 2n plus x minus z, and Charlie the color of n plus 2x plus 1. So how many bits does it take? Depends on how many colors you have. We have 2 to the root log n colors. So the number of bits needed to announce the color is root log n, right? Because we are using this color. Okay. So maybe you do it with, let's say, 6n, it doesn't matter really. Okay. Because these numbers are all 2n plus x plus y or whatever. We have range. I don't care about the constants. So it's just O of root log. Okay. But why is this a good protocol? Well, if the checksum is actually satisfied, x plus y plus z equals n, what should happen? So they announce the color and they check if all the colors are the same. That's the protocol, right? So maybe let me write that down. If all colors are same, say checksum equals 1, else say checksum equals 0. Okay, that's the protocol. So the number of bits of communication is the number of colors, which is O of root log n. And why does this work? Well, if the checksum is 0, checksum is n, this gap, this d is actually 0, right? So what does this mean? That means all 3 numbers are exactly the same, right? I'm adding d here, which is 0, right? So I have 3n here as well, 3n here as well, right? So this d is 0, so all 3 numbers are exactly the same, Okay, so the colors will be the same. If the checksum, if x plus y plus z equals n, the protocol will say, yes, checksum is 1. Okay. So y correct. So if x plus y plus z equals n, then all numbers are the same. So implies all colors are the same. Okay. Now, what if else if x plus y plus z is not equal to n? Then what should happen? D is non-zero. So we have a non-trivial 3AP. And if it's a non-trivial 3AP, they cannot have the same color. Right? Because by definition of our coloring, I cannot have 3 distinct numbers which form a 3AP in the same color class. Right? So then the numbers cannot all have same color. Right? Why is that? Because we know that there is no monochromatic non-trivial 3AP. That's why we built the coloring. Okay. So implies protocol says okay, so we are computing the right answer. Yeah. For this coloring, this one or this one. So this is coming from Behrens' construction. So we know Behrens showed that there is a set where this R3 of n is basically n over 2 to the root log n. Right? So I just substituted that, and when n over 2 to the root log n, the 2 to the root log n goes to the numerator, the n cancels. And because I have the big O there, I'm throwing away the log. Okay. So, I mean, we didn't prove this part, but it just requires working with Behrens' construction directly, or kind of proving this meta statement that no matter if I find a 3AP free set, I can also get a color. Okay. It's a very clever protocol, right? So find a coloring and then just announce the color of this weirdly computed numbers. So it's like a rabbit out of the hat. As I said, the protocol is very simple. Just a few lines. You compute these numbers, announce their color, and then you're done. Okay. All right. So in summary, what did we show? Okay, we showed that the NOF complexity of checksum on n is O of square root log n. Okay. And you might wonder, okay, what's the actual answer? Is this the right answer or not? Okay, this is from 83. And the best we have on the other end is that this is omega of log n. And this is due to Shkredov in 2006. Okay. So there's almost like a doubly exponential gap. Yeah, log n versus square root. Yeah. So yeah, we are kind of skipping this conversion. right? Right, but we don't think we can improve on Barron's construction, right? So in fact, that's a very good point that, you're right. If you could improve Barron's construction, then you could potentially have gotten a better protocol here, right? But, in some sense, what we knew from 23 is that this approach cannot give a protocol with complexity better than log n to the 1/3. Because it's kind of a weak, some kind of a lower bound, but these kinds of protocols, right? From these kinds of protocols. But still, the space of protocols is so vast. They build this, they pull this rabbit out of the hat in coming up with this protocol. That's still the best we have. But maybe there's something else you can do. I see Y and Z. Why should I only look at like this linear sum? Maybe I try something crazier. Who knows, right? And that's kind of the difficulty here, right? So somehow once you have inputs overlapping, we have very few techniques to understand complexity. Okay. And I said, showing this triple log is highly non-trivial. It requires some, many things for number theory, Fourier analysis, and all the other stuff that people tried for the 3AP problem. Okay. But at the, if you peel that off, you just have a communication complexity question that we are trying to answer. Right. And if I put 4 players or 5 players, then this log's just like, you're going to add so many logs, it's going to be somewhat embarrassing from the communication complexity side, right? But I said, even showing that the number grows with n is highly non-trivial. Okay. And it's also not a standalone thing. Like somehow there are many problems where understanding the Neberon Fourier communication complexity encodes very difficult and long studied problems in math. Okay, and also in computer science. That's one of the reasons when NOF is like the holy grail in communication complexity. Okay. All right. So for the next lecture, what I plan to do is the following, and then I'll tell you your 2 options. Okay. For the next lecture, what I'm going to do is first prove basically a weaker version of a similar question. A similar question, but in easier context, right? Okay, what is the easier context? So if you think of what we asked, right? So we said we want R3 of n was the min size of S subset of n. S has no non-trivial solutions to A plus B equals to C. Okay, non-trivial means distinct. Now this, we are doing A plus B equals to C, right? So you're looking at addition. So why only look at capital N? Okay. So what we are going to do first is study this problem in an easier context, in the sense that instead of looking at integer addition, we're going to look at modular arithmetic. Okay. It's easier to satisfy equations over mod 3, for example, right? So presumably you can understand it better than understanding it over the integer. Okay. So that's the thing that I'm going to talk about. There we now have at least a very beautiful solution. Okay. So let me call it, cap 3 of little n is, and I'll define it more formally again next time, but min of size S subset of 0, 1, 2 to the n. S has no non-trivial solutions to okay. I can't ask addition over mod 2 because then 2 times C becomes 0, so it becomes trivial. So the next the sort of the the least non-trivial question is over mod 3. Okay. So how many bits, strings can I find over 0, 1, 2 to the n such that a plus b doesn't equal 2c for any 3 elements in that sentence? Okay, I'm just doing addition over mod 3, right? So this is what we're going to talk about in the next lecture. And here, we know it's at least 2 to the n. If I take all strings which are only zeros and ones, then it doesn't have a plus b equals 2c at all. Okay. But we also know that this is at most like 3 to the 0.9. So we do get some substantial gap, and we will prove this in the next lecture. And the proof of this will involve something called the polynomial method. Okay, which is a beautiful algebraic technique where you use something about like properties of polynomials to encode some, function or thing that you're trying to prove as something about polynomials and prove this, use these properties of polynomials. Okay. So this, I think, will take up most of the next lecture, but for the last 3 lectures, either option 1 is more applications of the polynomial method. Or basically some details of okay. So we can either go into like the integer case more and see how you can get this sort of n over 2 to the log n to the 1/12. Can't cover the full details, but get at least tell you what are the main new ideas that are required to get this improvement. Okay. Or we can talk about other applications of the polynomial method. There are many, many applications. I can pick 1 or 2 and kind of present them. Okay. These are the 2 options. You can even decide it after the next lecture. Okay. All right. So with that, let me stop. And remember, tomorrow at 6 p.m., the exam will be released. Do not forget that. And good luck with it.